This video will cover a circular motion which I created for my IB students. We have horizontal and vertical circles. Please take a moment and read the success criteria I plan to cover in this video. So I have a picture here of an amusement park ride, and what you do is you walk in from the outside and you can see the girl here. She stands against the wall. You can use the links below to see the full video on YouTube if you'd like. What happens is when you stand against the wall, the whole cylinder on the outside will start to rotate. And as you see in the picture on the right, the floor actually drops out. They feel like they're being pushed against the wall, but that's not really the case. As they start to spin, it goes faster and faster with the wall beneath their feet, and then eventually it drops out. So let's think about what actually is going on, because if they're moving in a circle, there must be a centripetal force. But what's actually causing it? In this case, it's going to be the normal force from the wall, because remember, a centripetal force has to be towards the center of the circle. And so as they're spinning around their body with Newton's first law, we would say it normally would travel in a straight line. The second law says it'll stay in a straight line unless there's an unbalanced force acting upon it. So the centripetal force is that net force. Something has to cause it. It doesn't happen all on its own, and in this case it's the wall pushing them in that's going to stop them from traveling in that straight line and give them circular motion. So why is there a floor there at the beginning, and it's needed, and not now once it starts to spin? Well, there must be some friction against the wall, because in this case they're not accelerating up or down. So again, the forces must be balanced. So we have friction moving upwards and our force of gravity pulling us down. Now how does this change as we move faster and faster? Well, our centripetal force must be getting greater and greater. Remember, that was the normal force from the wall acting on the person. It's getting greater as the speed increases. And we also know that here's our equation for the force of friction. Friction is proportional to the reaction force, or I've written here as the normal force. That means there's greater friction as the cylinder spins faster and faster. When it's at lower speeds, it's not enough to hold you up, but once it goes faster, you're going to be stuck there. So let's look at some other examples of centripetal motion. Now first, I just want to point out, remember, centrifugal doesn't exist. There is always something causing a force towards the center of the circle to make it travel in the circle. The force must be there or our object would be traveling in a straight line. Nothing's actually pulling it out of the circle. It's not a centrifugal force. If you actually think that's happening, you must be accelerating and not realize it. For example, if you're in the back of a moving van without windows, when the van turns left, you might think you've been pushed to the right, but compared to the ground around you, you're actually still just going straight. You just don't realize it because you're in an accelerating frame of reference and you don't see it with no windows. Let's look at this one in the middle first. In this case, our centripetal force causing it to travel in a circle will be the tension in the string. As the person swings this around in a horizontal circle, then all we have to cause this force is the tension in the string. But it could be like this diagram here on the right. Notice now the tension right here. It now has a vertical component and a horizontal component. It's actually only going to be this horizontal component here that's going to cause our centripetal motion. In this case on the left, we have a roller coaster ride. We don't have a direct contact between the center of the circle and the roller coaster cart, but we know since it's traveling in a circle, there must be a centripetal force. In this case, we have the force due to gravity pulling down, as well as the normal force pushing from the track onto the cart. One thing to note in this diagram, the cart is on the underside of the track, so that means the normal force is pushing on the cart. We'd have a different example if the cart was riding over top of the hill. We'll see one of those later. You may have done this or seen this before. Using a bucket of water, if you spin it fast enough, the water will not pour out of the bucket as it rotates. In the top and the center here, we've got a car and it's going around a circle. Again, it might not look like there's a force towards the center, but it must be there if we're going in a horizontal circle. In this case, it must be from the friction between the wheels and the road. Pay attention to what direction these arrows are pointing here, towards the center of the circle. In the picture on the right, we have the force due to gravity that's attracting our satellite towards the Earth. We'll even do more work with the force due to gravity in this kind of situation later on in this topic. In the bottom, I have another example of the roller coaster. And here I really like this picture because it's going to show you all the different ways we could be talking about centripetal motion. In this case, with the car going over top of the hill, we still have centripetal motion towards the center of the circle, but now the direction of the normal force will be upwards. And it's one of the reasons why when you go over the hill, you feel like you might be coming out of your seat. There's still the force due to gravity downwards, but the net force is less than the case over here. Without a net force causing us to move in a circle, you would travel in a straight line and leave the track. Right here on the right, we have the normal force pushing us in the same direction as the centripetal force. It's causing the centripetal force with the force due to gravity. And in this case, you're going to feel like the seats are pushing on you. And finally, here's something I usually do in the second year of IB. It's due to the motor force caused by an electron or a charged particle moving in a magnetic field. One other one I could have showed, I could have also included the attraction between an electron that's negative moving around a positive nucleus. There's lots of other examples. So let's look at a couple of examples. Let's start with an easy one. A 200-gram ball is rotated in a horizontal circle with a string of 1.2 meters. If the maximum force the string can withstand is 50 newtons, what's the maximum speed the ball can reach? Okay, so let's start with our equation for centripetal force, mv squared over r. In this case, the centripetal force is going to be caused by the tension, which we know is a maximum of 50 newtons. If you notice here, I have written my mass in kilograms, and that's because hidden inside those newtons we know are kilograms, meters, and seconds. So if you left it as grams, you're not going to get the correct answer. So if we substitute in our values and then rearrange them to find V, go ahead, try it out. Don't just wait for the answer. I got a value of 17.3 meters per second. Let's stop and think for a second. Does this seem realistic? How many times would it actually make a circle each second? So, in other words, what's the angular velocity that would need to happen with that ball if it's doing a linear velocity of 17.3 meters per second? Let's calculate this out. Let's first use our equation to calculate angular velocity. That's going to give us a value of 14.4 radians per second. Now, that really doesn't mean much to me, so let's change that into revolutions per second. So if we're going to change the units here, let's do this by using unit dimensional analysis. So let's see, 2 pi radians is the same as 1 revolution. And I'm putting it this way because I want my radians to cancel out, leaving behind revolutions. Okay, so if I pick up my calculator, I'm going to get 2.3 revolutions per second. Does that seem reasonable? 2.3 times around in 1 second. Yeah, I think so. I think we could do that in real life. Okay, let's do an example with a vertical circle. Now, as it gets to the top in this case, we're going to have two forces pushing down on it. we have the tension in the string and the force due to gravity. So that means my centripetal force is going to be force due to gravity plus the tension. Now, it also asks then for a minimum speed the ball must have in order to make its complete arc. Now, if you've ever done this yourself, you know that as soon as you start going slower and slower, that ball will seem to drop. What that means is at our minimum speed, our tension is going to equal 0. So let's put this into our equations. Fc, that's mv squared over r, in this case for the minimum is just going to equal m times g. Notice the masses are now canceling out. I can rearrange this equation. V equals now g times r, and I need the square roots because I only want v. If you plug in your values, you should get a number of 3.3 meters per second. Now for part B, it says that we're at the bottom of the circle. So let's think about what's causing our centripetal motion. And now I've got the force due to gravity pushing downwards, and I have the tension pulling back upwards. So if I write my equation for the centripetal force, it's going to be T minus Fg. And because it's moving in a circle, we know that it has to be a net force towards the center. So tension must be bigger than the force due to gravity. It also said that we're now moving at twice the speed we had, so now we're going to say our speed is going to be 6.6 meters per second. So let's put some expressions in here. mv squared over r for our centripetal force, tension, and force due to gravity is m times g. Now, if I rearrange that, I'm going to get my tension is going to be mv squared over r plus mg. And let's put in some values and find the answer. I get 7.4 newtons. So let's look at that success criteria again. Hopefully now you can take the information from this video and our two examples and extend them to apply them to new situations so that you can say yes to the criteria.